Okay, today's lesson is on transforming equations, which is really just a fancy way of saying to solve for a specific variable. So when we are solving for a specific variable in an equation, we're going to do a couple things. The first is going to be to distribute, simplify, and get any like terms that we can all on one side so that we can combine them. So the most important of these, well, they're all important, but especially is distribution. If we see distribution just like when we were solving equations in our first unit, we have to do that distribution. Simplify it using distribution so that we can then hopefully combine like terms from there. Next, once we've simplified as much as we can, we're going to look to use inverse operations to isolate, meaning get our variable by itself. So whichever one we're being told to solve for, that's the one we want by itself at the end. So inverse operations undo operations. So for example, if your operation was subtraction, the inverse operation of that would be to add. So when you're using when you're using inverse operations, we will follow GEMDAS but backwards. So GEMDAS, if you read this way, from G up to S is the order of operations, and when we're solving, we go in the reverse direction, meaning we undo subtraction and addition first, then we look to undo any division or multiplication, look for undoing exponents, and we finish by looking to undo anything that was grouped together. So let's take a look at a problem. Here's our first one, and a strategy I really like to use when we're transforming equations is I like to circle or highlight whatever variable I'm being told to solve for. So if I'm being told to solve for x, I like to start by circling x to note that that's what I ultimately want by itself. I need to also take a quick glance at my equation and see if there's anything I can simplify here. In this case, there's nothing that can combine, so from here we're going to now move on to undoing the operations we're seeing occurring to the x and in the SADMAG order, meaning I need to first look for any subtraction or addition happening to the x. I'm adding a, so I need to subtract a from both sides. Well, a minus a is 0, so that will cancel out, meaning I just bring down the 3x. I could write a plus 0, but there's no need to do that. And over on the right side, we do not know a's value, so we'll just write 44 minus a. All right, so there is, if I continue to look for that x I want to isolate, there is no more addition or subtraction to undo around it, so we're good. We can move on to look for any division or multiplication. And so x is being multiplied by 3, so to undo that operation, I will divide both sides by 3. Now, the way you show this is very important, because if I'm dividing my left side by 3, I need to do the same thing to the other side to maintain the equality in our equation. And so the way to show that is to do a big division bar under both 44 and the a to show the whole side is going to be divided by 3. Well, 3 divided by 3 on the left becomes 1, so 1 times x is just x. And nothing can really simplify further on the right, so we'll just copy how we had it written. So x isolates to be equal to 44 minus a, all divided by 3. Here's our next example. In this equation, we're solving for n. So let's start by circling or highlighting that n that we want to ultimately isolate. We then look to distribute, simplify, combine any like terms, and at a quick glance here, I'm not seeing any of that can happen. But what I am seeing is that we have a fraction. And so we talked about last unit how to get rid of fractions and make nice whole or integer numbers in our equations. So I'm actually going to start in this equation by multiplying through by the denominator of that fraction. So I'm going to multiply every term in my equation, meaning anything separated by addition, subtraction, or an equal sign, I'm going to multiply by 3. So 3 times 1/3 xn, the 3 times 1/3 becomes 1 if I cross simplify there. So I'm just left with xn equal to, and then 3 times 5b becomes 15b. I'm still looking to isolate n, so from here now I have multiplication. I'll undo that by dividing both sides by this x that's left, leaving us with n equal to 15b over x. All right. Here's our next example. Before we do distribution, which I know you're dying to do, I hope so, notice we're trying to solve for y. So I'm going to circle every y that I'm seeing. And notice there are a couple, so we'll get to what to do with those in a moment. But the distribution has to happen first so that we can then simplify and then be able to isolate from there. So this gives us 2y minus 6 equal to 5y plus z. We're still looking to solve for y. However, I have y's on both sides of my equal signs. So to be able to isolate a y, we're going to need all our y's to be first combined. Then we'll be able to isolate them. So I'm going to combine these y's, and I'm going to do that by subtracting 2y from both sides. You could certainly have taken the 5y to the left, but to keep my numbers positive, I'm just choosing to subtract the smaller one. So this, I bring down the minus 6, will leave me with a 3y plus z on the right. At this point, I've combined all my y's, so now I have just one y visible in the equation. There's 3 of them, but right, that's the one we're going to be isolating. So now I can use my inverse operations to get anything being added to y or subtracted or multiplied to the other side. So we'll start by subtracting both sides by z. And then we will divide both sides by 3, leaving us with negative 6 minus z, all divided by 3, equal to y. You can leave your answer like that, or you may notice that negative 6 and 3 can divide out. It's important to note that negative 6 and 3 can divide out, however, z and 3 do not. So if you want to take it just a step further, you can divide the negative 6 and 3, but you have to remember that this is really a negative 6 divided by 3 minus a z divided by 3 equal to y, because every term should be divided by 3 on the left. So negative 6 divided by 3 is negative 2, and then you would keep the z over 3. So I would accept either of these answers. They would both be correct. Okay, here's our next example. And in this problem, we're solving for r. Now, the r is being squared, so we'll get to that in a moment. But before we can undo an exponent, if we're following SADMEG, we first look for subtraction, addition, and there's none of that happening to r. There is some multiplication. Both 4 and a are being multiplied by the r squared, so I'm going to divide both sides by the entire 4a. So that both simplified to a 1, leaving us with r squared equal to 5b divided by 4a. To undo a square, we take the square root of both sides, because the square root of a perfect square is itself. So r is just equal to the square root of 5b over 4a. This one we would not be able to simplify further because 4 is being multiplied by a. Even though you might notice 4 is a perfect square, because we don't know a, we can not take it any further. So that's our final answer. Okay, here's our next example. We want to solve for x in this problem. So I'm going to circle all the x's I'm seeing. So when you notice x's or whatever variable you're trying to isolate on both sides of the equation, you need to work to get them on the same side first. So get the x's on the same side. So that's our first order of business here. So to do that, I'm going to subtract 7x from both sides. And it doesn't matter how you do this. But that will leave me with an XA minus 7x. Notice I couldn't actually combine them because the x is multiplied by an a and this has just an x. So they're not like terms. So because I can't actually combine them, I'm just writing them together. I'll bring down my minus 2 and I'll bring down the b from this side. Okay. We are looking to isolate this x, and this is where this type of problem is a little bit more advanced because we were not able to combine our x's. So once you get the x's on the same side, anything that doesn't have an x, I want you to take to your other side. So let's add the 2 to the other side. So this leaves us with only terms with x's on the left and terms without x's on the right. And the reason this is helpful is because once we see that we have terms that only have x's, you will notice that both terms have a factor of x. So this is where we're actually going to apply reverse distribution, and we're going to factor out that common factor of x and then divide each term by x and leave what is remaining once that x is factored out inside of our grouping symbols. So xa divided by an x leaves us with an a, and 7x divided by x leaves us with a 7. Bring down the b plus 2. If you've done this correctly, then you'll notice we finally have just one x that can be isolated. So this is x times an entire a minus 7. To undo this understood multiplication, we divide both sides by a minus 7. The entire a minus 7's cancel out, leaving us with x equal to b plus 2 divided by a minus 7. So that is how we'll isolate an x variable if it shows up multiple times and can't be combined with another. Here's one to practice on your own, so I'd like for you to pause the video, solve for a, and then we'll come together and take a look at it. Okay, so you have solved for a, meaning hopefully you combined terms that did not have a's and brought over terms that did have a's to your other side. So I brought my 3a to the left and brought the 4 to the right. If you chose to do the opposite, that should still work as long as your calculations were correct. But we should end with a negative 13 divided by y minus 3. So the factor of a divided out, leaving you with a y minus 3. Divide both sides by that y minus 3, and that's how we'll fully isolate a here. If you had gone in the other direction, meaning you actually added 9 to both sides but subtracted a y, you would have been left with 13 equal to 3a minus ay. You would have brought down your 13, factored out the a, and been left with 13 over 3 minus y equals a. I want you to take a look at these two answers and notice that they are actually the same. While the signs are different, so this 13's, the numerator on the green 13 is positive, the one over to the right is negative. Those are opposite signs of each other. However, the denominator signs are also flipped from each other. So because every single sign is the reverse of the other one, it means they have a common factor of -1, and -1 divided by -1 is just 1. So these two solutions here are both accurate. So if you ever get an answer and notice every single sign in your answer is flipped from maybe the answer that's posted, do not worry, you have your answer correct. There's just going to be two ways to write these, and the reason for that is it depends which way you take your terms in the beginning, but they're all correct methods. And that is it for our lesson on transforming.